everyone, and welcome to the Biophotonics Discovery Podcast. Whether you're a seasoned researcher, a student just starting out, or you just love a good story about how light is used to solve big problems, this podcast is for you. We're making the discoveries in biophotonics accessible one episode at a time.
A New AI Path to Diagnosing Rare Pancreatic Tumors by Noel Daigle and colleagues. In a promising leap toward faster and more accurate cancer diagnosis, researchers have demonstrated that artificial intelligence can distinguish pancreatic neuroendocrine tumors from normal tissue using label-free microscopy images. This breakthrough could one day replace time-consuming histology workflows, speeding up clinical decisions and improving surgical outcomes. Pancreatic neuroendocrine neoplasms, or PNENs, are rare but increasingly diagnosed tumors that arise from hormone-producing cells in the pancreas. Their detection and treatment rely heavily on histopathology, painstaking manual analysis of stained tissue sections by expert pathologists. But this traditional method is slow, expensive, and highly dependent on specialized personnel, posing a challenge for timely surgical decision-making, especially when assessing tumor margins during resection. To address this gap, a team from the Biomedical Optics and Optical Measurement Laboratory at University of Arizona's Wyant College of Optical Sciences explored a combination of multiphone microscopy, MPM, a high-resolution, label-free imaging technique, and AI-powered image classification. Specifically, the team tested both traditional machine learning using handcrafted features and deep learning through convolutional neural networks, CNNs, to differentiate microscopic PNEN images from images of normal human tissue. The dataset consisted of samples from over 60 patients, processed either as formalin-fixed, paraffin-embedded, FFPE, or fixed frozen tissues, the two most common preparation protocols in pathology. Using MPM, the researchers captured images across 5 fluorescence channels targeting naturally occurring biomarkers, coenzymes like NADH and FAD, as well as structural proteins like collagen, without introducing any external dyes or stains. Their initial machine learning approach, which relied on texture features and linear discriminant analysis, yielded up to 87.5% classification accuracy for FFPE samples. However, the study's most striking results emerged from deep learning methods. The best-performing CNN, ResNet 50, achieved a remarkable 96.4% accuracy and an area under the curve, AUC, of 0.977 when trained on combined FFPE and frozen samples. Notably, this performance held across different tissue preparations, highlighting the robustness of the algorithms. Our models performed with high sensitivity and specificity despite variability in sample origin and preparation. Authors note. This suggests that digital pathology using label-free imaging could be feasible across clinical settings. The potential implications are far-reaching. With further development, this approach could usher in real-time, intraoperative tumor diagnostics, eliminating delays associated with slides, stains, and lab processing. By enabling rapid margin assessment during surgery, automated analysis might also reduce reoperation rates and improve long-term outcomes for patients with. Looking ahead, the team plans to expand their dataset, explore tumor grading through AI models, and move toward imaging fresh, unprocessed tissues directly. If successful, this technique could fundamentally shift how we detect and treat a variety of tumors using the body's own molecular signals and the power of machine learning.
If you enjoyed this episode, please subscribe, leave us a review, and share it with your colleagues. Your support helps us shine a light on the latest in biophotonics research. Stay curious, and we'll see you next time.